In this video, we're going to go ahead and solve this particular problem where you have an aquarium with water to a depth of 1 feet as shown here. To repair, we are going to replace a small triangular portion and we would like to know what is the resultant force on that portion, so that when we repair it with a strong enough piece. And so you see that piece on this vertical side out here. You're asked to determine the resultant force of the seawater on this area and the location of this force. Again, even though if it's not clearly specified here, they should have that it is open to the atmosphere on the top, and that's fairly obvious in this case, and of course it's open to the atmosphere out here. So there's a P atmosphere on the top and P atmosphere on the other side. From the inside you have pressure due to water. As usual, we have the problem number, given, find and figure. There is no need to draw this entire figure. We are really only concerned about the force on this triangular portion. So what we are going to do is we are going to draw that figure, and we typically draw the side view. So you are going to look at it from here. You're looking at it from here, so you just see this edge, this 0.3 feet edge. You will see the top surface of the water, and this is on a vertical line. So your figure is going to be, there is the free surface of the water, and then you have a vertical line, that's the side view of the tank, and your triangle is somewhere here. So let me draw a large enough figure. So let's say this is obviously not to scale. So this is the triangular portion that I'm concerned about. I don't care about the forces on this part of the tank, it's just the triangular portion. Well, what are all the distances from the top to the bottom? Is 1 feet. This height here is 0.3 feet. Notice that there is pressure from the water in here. On the other side, it's open to the atmosphere, so you're going to have atmospheric pressure on this side. There is P atmosphere at the top out here, and of course P atmosphere on the outside here. And we want the resultant of all of this. The view out here, when you look at it from this edge, when you look at it from here, is you're going to see the triangle. And the triangle is going to look like this. And this also is 0.3 feet. This is of course 0.3 feet. Notice the centroid of a triangle will be somewhere here. The resultant force of all of this, which is what we wish to find, is going to be somewhere below the centroid. That, let's say, is the center of pressure, somewhere below. Now for this particular problem, because there's P atmosphere on the top and on this side, we know it's this particular case. So I need to be using these set of equations, either these three or this and these two. I'm just going to go ahead and use these three. We're given all the values out here. The first thing to do is obviously to draw the coordinate axis, and that is the most important thing. This is the plane. This is the plane. Comes out of the plane of the paper. Y-axis is going to be along this, so the y-axis is going to be along this. So in this case, y-axis is vertical. Wherever the y-axis intersects the free surface of the fluid, that's where the origin is. And this of course is the z-axis. When I'm looking at it from this side here, I see this triangle. So I'm going to be seeing y-axis and of course the x-axis, which comes perpendicular to the plane of the paper. Now where do I position it? I can position it anywhere. I can position it anywhere. It just seems obvious to me that it just seems simple to me to just place it on this edge. So that's the y-axis. That's the origin. Of course, I'll see the x-axis in this view. You can place it anywhere. If you want, you can place it so that it passes through C. Wherever you place it, all the distances you calculate will be calculated with respect to the axis that you place. That's the first thing to do. Now we can go ahead and apply our equations. There is P atmosphere at the top and on other side this means that Fr is equal to just gamma yc sine theta times A. We know gamma yc is the y coordinate of the centroid. Everything is calculated from the origin. This is the y-axis, so the y distance of the centroid from the origin is going to be this height here. Sine theta, the angle of inclination of this plane is perpendicular to this. So the angle is, if you take the free surface, the angle from the free surface, the horizontal to this is essentially this, which is 90 degree. So theta is 90 degree in this case. And of course area would be area of this triangle. So what is YC? YC is this. We know this whole thing is 1 feet. I have to subtract this distance to get YC. Well, you know, for triangles, for any arbitrary triangle like this, you can see out here that the centroid is A by 3 from the bottom, where A is the height of the triangle. And this you should actually typically know. The centroid is always a third of the side from the base or the heel. So this whole thing is 0.3 feet. A third of that is going to be 0.3 by 3, which is 0.1 feet. So YC is nothing but 1 minus 0.1. So YC is 0.9 feet. Theta, of course, is 90 degrees. So if I go ahead and apply this here, Fr is going to be gamma. This is sea water, so notice that the gamma is different from normal water, which is 62.4. This is 64. It is denser. Pound per feet cube. YC is 0.9 feet. Sine theta is sine 90 degree, which is essentially 1. Area of a triangle is half base times height. Base is 0.3, height is 0.3, so the total area is in feet square. If you go ahead and calculate that, you're going to end up with 2.5920 pounds. That's the force on this triangular piece. We need to find out where it acts. It acts at P. So to calculate YR and XR, the equations are YR is YC plus gamma sine theta IXC by FR. I know YC already. I know gamma sine theta. I need to find the IXC. I already know FR. What is IXC for a triangle? IXC for a triangle like this is going to be BA cube by 36. So in this case, B is this base, A is the height, cube by 36. Here it is going to be 0.3 times 0.3 cube by 36. That is the base, height cube by 36. Units are of course feet raised to 4. So I know all of this. If I put that here, YR is going to be YC, which is 0.9, plus gamma is 64, sine 90 degree, which is 1, IXC is this whole thing, 0.3 times 0.3 cube by 36, divided by FR is 2.5920. And if you consider all the units will end up with just feet, and this is also feet, so the whole thing is feet plus feet. 0.9 plus 0.00555, let me just write 5 significant digits, that's what you have. So that is YR. What is YR? Again, all the coordinates are calculated from the origin. From the origin, in the direction of Y, the point where FR acts is so much. So this we've found out is 0.9. YR is greater than that, obviously, so that makes sense. You have to always check this. So it is greater than that by a tiny distance, so it is slightly down here below. So this here, from here all the way till here is YR, which is this. We need to calculate XR. XC plus gamma sine theta I X Y C divided by FR. Notice that I X Y C, B A square by 72, B minus 2D. Well, compare this shape with our triangle out here. If you compare this with what we have, D0, this A is 0.3, B is 0.3. So if you put those here, B is 0.3, A is 0.3, B is 0.3, D is 0, our IXYC will be 0.3 times 0.3 square, that is BA square, times B minus 2D, D0, divided by 72. That's nothing but 0.3 cube times 0.3. This goes away, so that's nothing but 0.3 raised to 4 by 72. Again, this is feet raised to 4. So if I go ahead and put that here, XC, what is XC? XC is the x coordinate of the centroid. That's the centroid. All the coordinates are measured from the origin. In the direction of x, XC is going to be this distance here. What is that distance? Well, again, the centroid of a triangle. In this case, for example, this is XC that I'm looking at from this edge. That's what is XC. B plus D by 3. In our case, D is 0. B is 0.3. So 0.3 plus 0 whole divided by 3 will be 0.1. feet plus 64, that's gamma, sine 90 degrees, IXYC, 0.3 raised to 4 by 72, FR we've already calculated. You will end up with 0.00277778, 1027 7 1 2 3 4 5. Like this becomes 8 feet. That is XR from the origin in the direction of X to the point P. So from the origin in the direction of X to the point P. That is what the question asks for. Now if you actually plot these points out here, notice that C is at a distance of 0.1 and 0.9. So the coordinates of this are 0.1 and 0.9. If you actually plot this exactly to scale, and then you plot P, the coordinates of P are 0.90556, that is Y coordinate, X coordinate is 0.10278. It will end up with somewhere here below and to the right, because XR is greater than XC in this case. XR is greater than XC is just 0.1. Then these 2 points actually end up falling along the line which connects the vertex to C. That is actually known as the median line. The line that connects the vertex to point C, this particular vertex, to the centroid. If you extend it, P just ends up being on that line. Just interesting to note. It can of course be shown, it can be proved that it will fall on that line, but I'm just showing it to you. That gives us all the 3 answers that the problem is asking for: FR, YR and XR.